Here's a grid. You start top left, you finish bottom right, and you can only move right or down. The question, how many distinct paths are there? Was for a tiny grid we can count them by hand, but make the grid bigger and the number explodes. We need a method. Let's state it cleanly. Given an m by m grid, start at cell 00, reach cell m-1, n-1. You may move only right or down. Count the number of distinct paths. Take a 2 by 3 grid. There are exactly 3 ways across. This is the cleanest 2D dynamic programming there is. Ask the key question, what changes between subproblems? Both the row and the column change. So our state is two-dimensional. Define f of rc as the number of distinct paths from the start to cell rc. The answer we want is f of m-1, n-1. Now the recurrence. To arrive at cell rc, your last step came from one of two places, from the cell above or from the cell to the left. It's a count, so we add them. f of r c equals f of r minus 1c plus f of r c minus 1. The base case, f of 0, 0 is 1 and any cell outside the grid contributes 0. If we compute this top-down f of r, c calls the cell above and the cell to its left. But notice, interior cells get reached again and again from many branches. Those are overlapping subproblems. The fix is classic dynamic programming. Store each answer once in a 2D table and reuse it. Here's the bottom-up version. Make a 2D table, seed the start cell with 1, then sweep row by row. Each cell is simply the sum of the cell above and the cell to its left, guarding the edges so we don't read out of bounds. Once the table fill in, every number is just a plus left. The bottom right corner holds our answer. Here's the key 2D trick. Look closely. Each row depends only on the row directly above it. So we don't need the whole table, just one row at a time. We keep a single 1D array and overwrite it as we go. In 2D dynamic programming, space optimization almost always means this. Collapse the full table down to 1 or 2 rows. Learn the move once, it repeats across the entire module. The complexity falls out immediately. There are m times n states, and each transition is constant time. So the time is order m times n. And after the space optimization, we only store one row, order n space. One quick aside. There's a pure math shortcut. The answer equals m plus n minus 2. Choose m minus 1. You're just picking which of your steps are the down moves. Nice to know. But the dynamic programming method is the transferable skill. Because the very next problems add walls and costs that break this neat formula. 2 pitfalls to avoid. First, out of bounds reads, always guard that r is greater than 0 and c is greater than 0 before reaching up or left. Second, don't mix up m and n. M is your rows, n is your columns. And here's the cliffhanger. Now drop some walls into the grid. How little does the code actually have to change? That's unique paths too, and it's next. To practice, count the paths on a 3 by 3 grid by hand, then verify with code. See you in the next one.